Hello everyone. Today I am going to discuss about I2C Communication Protocol. My name is Shankar. This is the agenda for today's presentation. Please take a look and continue to watch the video if you are interested. I will pause here for a while. I2C stands for Inter-Integrated Circuits. I2C is a serial protocol. So there will be two types of communications. One is serial and other one is parallel. In serial, there will be one data line connected between the transmitter and receiver, and data bytes will be sent bit by bit. In parallel, there will be multiple lines connected between the transmitter and receiver, and hence multiple bits per byte will be sent at a time. I2C requires two-wire interface between the transmitter and receiver, and it is used to connect low-speed devices. So the speed of the I2C bus is low. Devices like microcontrollers, EEPROMs, analog to digital, digital to analog, and I/O expanders can be connected to the I2C bus. I2C is a synchronous serial communication. Synchronous means there will be a clock between the transmitter and receiver, and serial means the data will be sent bit by bit. I2C supports up to 3.4 Mbps speed. The speeds can vary depending on the master and slave. So if the slave doesn't support higher speeds, the master cannot communicate at higher speeds with that slave. The standard speeds and the I2C bus communication are 100 kbps, which is known as standard mode, 400 kbps, which is known as fast mode, 3.4 mbps, which is known as fast mode plus. I2C is a master slave protocol. So there will be masters as well as slaves on the I2C bus, and master controls the transactions. I2C is a half duplex bidirectional protocol. Half duplex means the either only one device can communicate or can transfer the data. Either master or slave can put the data on data line, and it is a bidirectional means a master can read as well as write data to slave. Data length in I2C is fixed to 8 bits. So the data is a 8-bit length, and unlike in UART and SPI, the data length can vary from 5 to 16. I2C supports slave addressing, and there are two modes supported. One is 7-bit addressing and 10-bit addressing, and only two lines are required for communication. I2C bus consists of two lines, namely serial clock, which is also known as SCL, and serial data, known as STA. There will be pull-up resistors connected to these lines, and a device on the bus can act as a master or slave or both. And bus is entirely controlled by the master. That means only master can initiate a transfer between the devices. Multiple masters and slaves can also be connected on the I2C bus. Each slave should have its own unique address. If the two slaves have same address, then the communication between them will be difficult. A master can also act as a slave, and it can address itself. If you look at the internal diagram of the SCL and STA lines, there will be open drain pins. So open drain means if the master wants to drive the line, it can only drive the logically 0 on that line. So it cannot drive high. So high will be driven by the external pull-up resistor. So and hence pull-up resistors are necessary for I2C communication. I2C is a dominant zero bus. Means if two devices are trying to drive one and the other one is trying to drive zero, then logic zero will be seen on the bus, and hence it is called as dominant zero bus. The main advantages with the open drain pins are, suppose if any of the slave devices or master devices powered off, and there will be no power to the device, and open drain pins uh, cannot impact the bus. So the other devices may continue to communicate with I2C communications. So that's the advantage of open RAN pins. And some devices will implement fast open rain. Fast open rain is something like, suppose if the device is trying to drive the pin from logic 0 to logic high, during this transition the device will try to drive the high instead of leaving it open rain. So and hence the line will reach logic high quickly and it can communicate at higher speeds. The start and stop conditions. Our start condition is something is like when the clock line is high, if the data line goes from high to low, then it is treated as start condition. And if the clock line is high and if the data line goes from low to high, then it is treated as stop condition. So a start without a stop condition is treated as repeated start, and I2C bus is treated as busy between a start and stop condition, and no other master is allowed to initiate a transfer between start and stop. I2C frame is consists of the start and stop conditions and the data in between them. So data byte is 8-bit length and followed by a acknowledgement. So if the master writes data, then slave acknowledges that byte, and if slave writes the data, then master acknowledges that byte. In each byte there will be 8 bits. A bit is consists of a clock line low and then high. So during the clock line low, the data line is changed from. When the clock line is low, the data line will be changed, and when the clock line is high, the data line will be stable, maintained. So the other device can read the data line when the clock line is high. So if the slave doesn't support that speed, what it will do is it will stretch the clock line during the low phase, and then it will drive the data line to its desired value and then leave the clock so that other device may continue to read the data. I2C frames is consist of start condition followed by 7-bit slave address and then read write bit. If read write bit is 0, then it is master writes, and if it is 1, then master reads. Once the slave address is written, then if any slave is present with that address, it will acknowledge that data slave address, and then for master write, master will write 8-bit data followed by a slave acknowledgement, and then if master wants to finish the transaction, it will send a stop condition. For master read, start will be sent and then followed by a 7-bit slave address, and then read write is set to 1, and slave acknowledges that slave address, and slave sends 8-bit data if the master provides clock, and then master has to acknowledge that byte, and for the last byte master sends nag and followed by a stop condition. This figure shows the master state machine. So if you are implementing a master write or master read, the following states will be occur depending on the state. Suppose if start is issued on the bus, then it will you will receive one state, and if slave acknowledges, you will receive one state, and if slave doesn't provide any acknowledge for the address, you will enter into one state. If the arbitration is lost, then it will enter into another state. So one has to address all these states, and one has to handle all these cases for master. If you are implementing a slave, then these following states will be occurred. So one has to implement the state where the slave responds with ACK or NACK for the slave address, and one has to implement for the data byte acknowledgement, and one has to implement for the general call address. Now general call address. So general call address is something like it is common for all devices, and mainly address 0 is used as general call address. Suppose if the master wants to communicate with all devices or all slaves at the same time, then general call address will be used. It is only used for writing data to all slaves. It can't read data from the different slaves, because if different slaves are trying to write a different data, it will be corrupted. Master does not actually know how many slaves are responding for the general call address. It can only know whether at least one slave is responding for general call address. Bus arbitration. When the bus is idle and if one, two or more masters are trying to initiate a transition, then what will happen is they will both see send the start condition at the same time, and bus also will be seen with the start condition followed by data put by the different masters. And suppose if any conflict between the data put by these two masters, then the bus line will be seen as different. Suppose if one master is trying to put logic 0 and other is putting logic 1, then definitely I2C is a dominant 0 bus, and 0 will be seen on the bus, and the one which doesn't see its value on the bus, it will go into arbitration last, because the value it has put is not seen on the bus. So say arbitration last can happen at any phase. During slave address it can happen, during read write it can happen, during the data phase also it can happen. So bus capacitance. Bus capacitance is like, so we have clock and data pin side. So each device will have its internal capacitance between the pin and the ground. So this capacitance will play a major role in the rise time and the pull-up resistor calculations. So if you calculate the pull-up resistor, the minimum value will be VCC minus low level output voltage maximum, that is accepted by all devices in the bus, divided by low level output current. So that will give you pull up resistor minimum value. If you calculate for the maximum value of the pull up resistor, it will be equal to rise time divided by 0.8473 into bus capacitance. So if the bus capacitance is more, then you have to put your maximum pull up value will be lesser. And so since it will be a RC network, the rise time for the RC network will be R equal proportional to R and C. So if the C is higher, definitely rise time will be higher, and bus will take higher time to reach logic high, and hence the bus cannot be operated at higher speeds. Clock stretching. Suppose if the slave is not ready with the data that was requested by the master, what it can do is it can stretch the clock so that the master waits for the slave to release the clock, and then the master can continue to provide the clock again to read the data. So since I2C is a dominant 0 bus, and if the slave wants to drive the clock low during the low phase, it can extend the clock low. So this is called clock stretching. This is mainly used when the slave is not ready to respond, or if the clock speed is too high for the slave to operate. I2C bus extenders. I2C bus extenders are mainly used to extend the I2C bus capacity. Suppose If the bus capacitance is increased and if you want to communicate or connect more number of devices, we can put extenders in middle so that these extenders can drive the bus. It can also be used for level translation. That means if one side it can be a 1.8 volts and the other side it can be a 3.3 volts. I2C bus multiplexers. So the main use of multiplexer is, suppose if two devices are there with same slave address and that slave address cannot be changed or cannot be programmed, then what we can do is, and if there is a need to connect those two devices to a same or single I2C bus, what we can do is we can put a multiplexer in between, and we can select any channel through this multiplexer, and we can communicate to each of them individually. So this I2C bus multiplexer will have its own address and it can be addressable through the same I2C bus. Once the channel is selected, whatever master is trying to send on the main bus, it will route that data to the selected channel. Logic analyzers like Select logic are used for capturing the I2C and analyzing the I2C bus data. So there will be I2C analyzers that are available with Select logic, and that can be used for analyzing the data that was sent. And we can also write our proprietary protocols on top of this I2C and the Select logic itself to decode the proprietary protocols. And hardware I2C spy host adapter can be used to exercise master or slave or both I2C communications. The main commonly faced issues in I2C communications are there may not be pull-up registers are present. Suppose if there is no pull-up register, the bus may not work. And I2 SCL and SDA lines are interchanged between the master and slave. If it is interchanged, we need to swap those lines. And if there are having conflicting address between slaves, then we may need to change their addresses if possible. Otherwise we may need to use multiplexers. And if there is excessive bus capacitance and that makes impossible for the line to reach logic high, then we may need to put bus extenders, or we may need to connect some other devices to a different I2C bus. If there are some spurious glitches or noises on the lines, on the clock and data line, then those glitches may be treated as a start condition by the master as a slave. And if it is treated as a start, then it may enter into busy state unwantedly or unnecessarily, and it may not be useful for communication. So one has to look for those glitches and one has to reset the master and slave all devices on the bus to be able to communicate. Thank you for watching my video. If you have any comments or suggestions, please do comment.